Okay, so hello everyone. Welcome back to the Sustainability Podcast with the Nevada Conservation League. My name is Evan Gatesman, and we're looking to create conversations around sustainability. And we're with the Nevada Conservation League, who is the independent political voice of Nevada's conservation community. And we work to maintain and enhance the natural character of Nevada and the quality of life for Nevadans through effective advocacy, the election of pro-conservation candidates, and building collaboration. And today it's my pleasure to introduce our next guest, John Hoaglund, who I originally met at an electric car show at the Springs Preserve. And today's topic is going to be carbon sequestration. So that's pulling carbon out of the atmosphere and storing it in some kind of static state, right?
Yeah, that's correct. Trying to get carbon into a solid state. And I should say there's two kinds of technologies that are involved in that whenever you discuss carbon sequestration, and that is pulling existing carbon out of the atmosphere. That's called DAC, direct air capture. And then there's FSC, which is flue stack capture. So one is designed to get carbon out of the atmosphere, and the other is to prevent it from going in the atmosphere in the first place. And as the name implies, flue stack, that's generally, industrial releases of carbon gases, not necessarily tailpipe, right? So that's a separate issue. Trying to sequester that carbon is different. But yeah, that's basically trying to take carbon in a gaseous state and turn it into a solid. And in my case, mineralization, you can create other types of carbon solids, carbon fiber, carbon, well, for that matter, even biotic or plant material. But the other option is to just condense CO2 gas and do something called underground injection, at UIC, underground injection control. And there's been a lot of projects involving trying to sequester CO2 as a fluid, as a gas, as a condensed gas, and using it even as a fracking fluid underground. That's another approach. There you're not really creating a solid, but you're sequestering it underground. So does that make sense? Those are a couple of ways to lock up carbon.
Interesting. So in general, why do we want to store carbon? Like, what is the overall goal?
CO2 is one of several greenhouse gases, but it's the most abundant in terms of, in terms of its effect, just because of the combination of its efficiency at re-radiating heat as well as its abundance in the atmosphere. So it's one of the largest greenhouse gases, and it's creating climate change, of course. So the idea with both, preventing carbon from getting in the atmosphere in the first place, trying to contain industrial emissions of carbon, as well as pulling existing carbon out of the atmosphere to try to reduce the man-made component of the greenhouse effect.
Absolutely.
There's a natural greenhouse effect, and that's what's confusing to the public. There is a greenhouse effect on Earth that even if humans and industry were not here, there would be a greenhouse effect that raises the temperature of the Earth, just absorbing free radiation from space. It would raise it up something like an average temperature of 50 degrees Fahrenheit or something like that globally. But we've increased that by our human-induced climate change. So that's what we're trying to head off.
Okay, so we're basically trying to store carbon to counteract global climate change caused by human sources as opposed to the natural sources.
But right, and yeah.
So how does that work as far as are we also trying to counteract the Earth's forces at all? Like, would that benefit us or not really?
Well, I could go at length on the carbon cycle. By the way, my background is in geology, and I was teaching climate change at the University of Michigan. In fact, I was teaching the graphs that Al Gore ended up using in his movie, An Inconvenient Truth, which show, well, some of the graphs were the increase of CO2 measured in Mauna Loa, Hawaii from 1950 forward, as well as some of the climate reconstruction graphs that were pulled out of ice cores in Antarctica. Several of my colleagues actually worked on that work in Antarctica, namely Richard Alley. He's a big name in the climate change debate in academics. There's certainly a natural carbon cycle, and I think that's part of what people have to understand, because when you see counter arguments to the idea of human-induced climate change, they'll say, well, volcanoes emit CO2, or there's CO2 exchanging with the ocean, and there's all these different factors, and yeah, that's in there, and we accommodate that. There is an uptake of CO2 into the oceans, and we can enhance that. In fact, one possibility of increasing carbon sequestration naturally has been to fertilize the ocean, and I'll talk about that a little later, I think. Kind of a spin-off of what I'm trying to do. And in fact, in some of the things, the permanent sink for carbon is as carbonate mineral, and that's actually what I'm trying to promote.
Right. So that's like seashells, right?
Well, yeah, you could call it seashells. It's solid carbonate mineral, whether that's in seashell or just lime deposit on the seafloor is lime mud, but most of it is either macroscopic shells, but a large majority of it is actually microscopic shells, plankton and zooplankton producing shells that are precipitated, as we call it in geology, the ooze, right? So we deposit ooze on the seafloor, and that's ultimately carbon getting onto and getting deposited onto the seafloor is carbon's ultimate fate on Earth, at least in the million-year time scales. Now, then at that point, carbon then is subducted and re-released as volcanic CO2 gas coming out of volcanic vents. But by then, it's had interaction with the mantle and everything like that, so it's got a completely different chemical signature. So, and then of course, some of the carbon, particularly marine carbon, gets incorporated into organic carbon, which ultimately becomes either methane. There's methane deposited on the seafloor, and of course, ultimately, there's also a source of petroleum. That's ancient organic carbon that's been buried as well. But carbonate mineral is the permanent sequestration of carbon, for the long-term storage of carbon out of the Earth's atmosphere and into the ocean.
Yeah. So you said one way of sequestering carbon is to basically to feed the ocean in some way, but in your website in general, you talk about using salt water to store carbon in general. Is that the same, or is that a different process?
Well, yeah, mine is an industrial mimicking of that process, and really kind of a mimic of what the Earth does. It's an industrial mimicking of what the Earth does naturally. It raises the pH of a fluid. So the first step in the process of electrolyzing seawater is to produce a base. In the case of the seawater electrolysis, it's sodium hydroxide, and then you aerate the water with CO2, and that forms a dissolved compound of carbon called bicarbonate. And bicarbonate is very stable in water, and calcite is in shells, and it's in microscopic organisms, as well as in just naturally occurring carbonate precipitate. So if you can get calcite to be precipitating on the seafloor, that's ultimately putting carbon to rest on the seafloor. Now, the industrial process is that I'm trying to promote is two phases. And by the way, I should say I don't have the patents on these. I'm working with a company that has patents on these. Actually, there's several that are doing variations on this theme, and I'll get more into that maybe a little later. So the idea that I had would be to take this carbon sequestration process and marry it, couple it, what is the word that I want, to the desalination plant, the desalination proposal. There's a site in Huntington Beach, which is site of the AES power plant at Newland and PCH, and Poseidon, which is a water company, is building a desalination plant. I don't know, they're going through various approval processes right now with the county and everything, but it's been on the books since like 2000. But I think they've been given the final go-ahead to build this plant now, and they've built them before in Carlsbad, California. And anyway, the plant, the desalination plant, is sitting right on a power plant. So it's sitting right on a CO2 emitter. They're sharing the property. And then the desalination plant is drawing ocean out of the old water intakes for the power plant and then sending the brine out to sea. So rather than having these two polluting industries sitting side by side, the idea was take the CO2 emitted from the power plant, run it through this electrolyzed salt brine that you can produce from the brine that's produced from the desal process, and in the process store carbon, or at least sequester it into solid form. So that's the mimic of the Earth's carbon cycle, is to try to get carbon into bicarbonate, into either in solution as bicarbonate or ultimately into solid carbonate mineral.
Yeah, which is also a naturally occurring process, obviously. Like you go to the beach, you see the seashells, right?
Yep.
So we talked a lot about carbon in general and carbon sequestration, but I've heard actually that methane stores more heat than carbon. It's just in a smaller quantity in the air. So
That's
can you
correct.
tell us a little bit? Can you tell us a little bit about methane as a greenhouse gas and kind of what threats that produces?
Well, I can talk a little bit about it. Yes, it's a much more efficient greenhouse gas molecule, but you said it, it's in a much less concentration than CO2. So much so that it really doesn't factor in at least human production of methane. I mean, there's some methane byproduct from animal operations, for instance, and there's certainly natural gas production. But one of the biggest threats to the climate right now is, as the northern hemisphere begins to thaw, you're releasing methane that was locked up in the permafrost. So the reason methane's coming back into the fore is it's a feedback. Think of a snowball rolling down a hill. The bigger the snowball gets, the bigger the snowball can pick up snow. And that's the same kind of thing that's going on with, as the climate warms, it is affecting the northern hemisphere more than any other place right now. And that is then melting permafrost that had locked up methane. And so now methane is going up into the atmosphere in ever higher concentrations than it had been before, and is a much more efficient greenhouse gas. But if we want to look at the human sources of methane, the largest sources, of course, natural gas production from petroleum, that's methane, CH4. Or any operation that involves animal waste. Cafes, what are they? Concentrated animal feeding operations, or CAFOs, not cafes, CAFOs. Concentrated animal feeding operations. You want to eat at a cafe, not a CAFO. Ironically, and this is something that I wanted to bring forward really fundamentally in the climate issue. We can look at CO2 as an emission issue from automobiles, transportation, and energy in general, burning coal, burning natural gas in power plants, that kind of thing produces CO2. But there are other industrial sources of CO2 as well as methane, but for the most part, the methane gets consumed. It's either burned or it's converted into something else. And the two biggest CO2, well, I can't think of any industrial process that involves heat and doing some chemistry that doesn't kick off CO2. I mean, steel making, you name the process, it seems like CO2 is always a byproduct. It's certainly a byproduct whenever you're burning any fuel. But one of the biggest industrial sources of CO2 that people don't think about is cement. I'm talking about, the standard cement production. Because what is cement? Well, okay, the raw material for cement, they take limestone, which is the very thing that I'm trying to produce and put on the ocean for, is the calcium carbonate lime. That is from ancient oceans in the Earth's geologic past. There are limestone deposits which are very pure calcium carbonate, precipitated millions of years ago in a bedrock type called limestone, which is almost 95% calcium carbonate. They take that as a raw material, and one of the things that they do is calcium cation, and then carbonate, which is carbon and 3 oxygens. What they do is it's called calcining. They heat it, they bake the limestone, they drive off CO2, and they're left with CaO, calcium oxide. What is calcium oxide? It's better known as Portland. It's cement. So in the production of any kind of cement, any kind of concrete, you're producing lime, and you're talking about tonnages. I mean, you've picked up a Sackcrete bag, right? And it's a combination. Portland's a combination, or concrete is a combination of Portland, calcium. And they throw some other things in there for stabilizing, but it's basically calcium oxygen. And then they mix it with sand or aggregate. And that's your concrete or your cement. And in the production of that calcium oxide, it's coming from calcium carbonate. And in the process of doing that, they're driving off CO2. So this company that does have the processes for making this carbon sequestration technique, they're testing it right now, not on a power plant. Their original plan was to test it on a power plant. They're doing it right now on a cement plant in San Antonio, Texas. They're looking at, in fact, one of the problems they were having originally when they tried to do it on a power plant is that they, in addition to carbon dioxide production from burning the fuel, you also have water. You produce water. You burn a fuel, you produce water and CO2. That's the bottom line. I mean, we even do that. We burn sugar, we exhale water and CO2. Cars do that. Everything does that. Well, in a power plant, they were having problems with the water in the exhaust, if you will, or in the flue stream, getting in the way of the process. They're trying to figure out a way to perfect that, to make it work in a more general environment. But in the meantime, they moved over to a cement plant because that's just CO2 emission. They heat up the calcium carbonate, and they produce calcium oxide, and they drive off CO2. So cement plants produce tons of CO2. And another huge operation that produces CO2 is the production of ammonia fertilizer. And this is absolutely critical that the general public understand this in terms of sustainability. I always recommend this article, and I think the whole world should read it. It's called The Oil We Eat by Richard Manning. He's an ecology professor, and he wrote this article back at the time of the Bush Gulf War II, Roman II. He wrote Tracing the Food Chain Back to Iraq, and he was talking about the oil production that methane, which is natural gas, byproduct of oil production, but also natural gas is sometimes sought just on its own. Anyway, that natural gas goes into a series of plants along the Mississippi River, primarily in this country, but elsewhere, performing the Haber-Bosch process. And the Haber-Bosch process takes methane, CH4, plus nitrogen out of the Earth's atmosphere and produces NH3, which is ammonia. And ammonia is fertilizer. So in the production of fertilizer, now the process of that, it's actually, you basically think CH4 and replace the C with N. Get the carbon out of the molecule, put nitrogen in there instead. So you're producing NH3 or NH4 as ammonium, and you're driving off CO2. And it's called the steam reforming process of the Haber-Bosch process. It takes high temperature and pressure to do it. So first they're using a tremendous amount of energy, heat, and pressure, and then on top of that, they're using natural gas as an ingredient to produce ammonia, and at the same time liberate CO2. So you have CO2 production coming out. And I think Richard Manning says 40% of the world's population eats only because of the production of ammonia. It's that critical of a fertilizer in industrial agriculture. That 40% of the world's population depends on this ammonia production from these Haber-Bosch plants, and they're CO2 emitters. They consume methane, which is a good thing, but they produce CO2 as a result. So anyway, I could imagine that this process that I'm talking about of trying to capture the CO2 out of the flue stack could be applied to these plants as well. So you can get cement plants, the Haber-Bosch ammonia production plants, and just about any process that liberates CO2 could take advantage of this process.
Right. So after you said that CO2 is pretty much created by the production of everything.
Yeah.
Is there some way to like tackle this legitimately, or do you think?
Well,
I mean, some people think this is the metaphorical train that we're putting our heels down to stop. Do you think there's truth to that, or do you think that this is a accomplishable thing and a tackleable problem?
I think we have to develop the techniques for doing it. Let's go back to a more fundamental level of chemistry. What's going on? You're taking almost everything that we touch and feel and see and eat, and everything is a carbon compound. Plastics, your food, pharmaceuticals, the oil and gas you put in a car. A lot of the stuff we manufacture is carbon based, and we produce a carbon product that we want to use, and then ultimately we get rid of carbon waste. The carbon waste that we produce, CO2, is in its most energetically stable situation. So entropy is maximized, if you remember the concept of entropy in chemistry. So if you're going to take a compound like CO2 and produce something useful out of it, it's going to take energy to do that. It's always, now, anytime you produce something, it's going to take energy to run the reactions. Even making plastic, you got to take some kind of crude oil input, and then you perform some heat to it or some chemistry to it, and you produce plastic or whatever. You're taking an organic molecule, producing something useful, and you're driving. I'm sure you're driving off in that process too. You're driving off some form of CO2. We can produce a technique for entrapping that CO2 and sequestering it. It takes energy to do it. Why is it? I mean, even collecting up CO2 that you have liberated gaseous CO2 coming out of let's say a steel plant or a power plant smokestack or something like that. That CO2, if you decide that, okay, all I'm going to do is concentrate this and pump it underground, which so far has been the main answer when somebody says carbon sequestration, that's really what they think of right now. I mean, mineralization is sort of given a second look at, oh yeah, there's that too. But by and large, most people say, well, we've got the CO2, if we can concentrate it, then we can inject it underground. In other words, they look for a trap underground where they can try to store the CO2. But even doing that, you have to take a gas, which is, energetically a loose, stable particle, molecular arrangement, right? It's evenly distributed in a room, it's spread out to the shape of its container, like all fluids. You have to then concentrate that. So right now you're talking about energy, you're talking about pressure volume work to concentrate that gas down into something that you can then pipe, or pump to the field that you're going to inject it underground. So even collecting the CO2 out of a relatively concentrated area, like out of a flue stack, getting it compressed, getting it into a fluid that you can pump, and then injecting it underground, that takes energy. So anytime that you're going to produce anything useful out of CO2, it's going to take energy to do it. And so it ultimately then becomes a cost-benefit analysis of, where you're expending energy anyway. And I haven't run those numbers, but I think what I'm trying to do with desals, like, you're already spending tons of energy to concentrate that salt. I mean, that's not your goal in desal. Your goal in desal is to produce the fresh water, but the energy is going into pumping salt water through a membrane to produce fresh water as a result of that. You can almost think of that analogously as the energy of evapotranspiration, or evaporating the water, fresh water, off of a salt source, the ocean. That takes energy to do that. So it takes energy to produce a fresh water, right? But you also have this salt. So the net effect of expending that energy to produce fresh water is this concentrated salt product. here is a way that you can take this liberated gas, run it through that, and immediately trap it into the water, as bicarbonate, and then ultimately into carbonate mineral. And that, to me, I think, if you have, especially if you have those things working side by side on the same property, that could be energetically feasible. The process that I'm describing here of electrolyzing salt, we're right there. There's the energy that's input. That reaction is not spontaneous. It takes energy to do that. You literally put salt water in what's called an electrolyzer. It's an anode cathode arrangement. You add an electric current to that. You're producing you're producing the products that I'm talking about, the sodium hydroxide, the hydrogen, and chlorine. And then separately, you're running through the CO2 through that solution and producing bicarbonate. That process is spontaneous. In fact, Dow, one of the ways that I discovered this reaction on paper is I was reading about Dao Chemical, which was located in Michigan, and they were producing brine, and they were electrolyzing, forming sodium hydroxide. They sell it as a product, the sodium hydroxide. So they were electrolyzing brine out of the Michigan basin and producing sodium hydroxide. And they had some papers describing what they had to do to securely ship the sodium hydroxide so it wouldn't become contaminated. And I began digging, well, what's contaminating this sodium hydroxide? Why does it have to be airtight? Just atmospheric levels of CO2 alone, they're talking like the 315 part per million that I was talking about, the ambient CO2 concentration in the atmosphere, was enough to taint the sodium hydroxide in their containers, because it would cause some of the sodium hydroxide to go to sodium bicarbonate, which is exactly what I'm trying to do. I'm trying to make sodium bicarbonate, which is baking soda, basically. To Dow, this is not something they wanted. They wanted to sell raw, unadulterated sodium hydroxide product. But because their vessels were leaking, they were ending up with sodium hydroxide impurities in this material. So that goes to show you how effective it is. Now, in fact, the idea of removing sodium, using sodium hydroxide to remove ambient CO2 has not been lost. I've been talking primarily about flue stack capture, taking CO2 in two industrial processes side by side and running them together. There was a guy, he's now at the University of Arizona. He started out at Lamont Doherty at Columbia University. His name's Klaus Lackner. And Klaus, I guess he's at Arizona State, not University of. And he has been working on techniques for doing that DAC that I was talking about, direct air capture, using chemistry that's actually sensitive enough to draw CO2 out of the ambient atmosphere, the Earth's atmosphere, right out of the atmosphere. So I could point you to that on the website maybe later and show you some of Klaus Lackner's work. So, but it just goes to show you that once you produce that sodium hydroxide base, at that point it reacts really quickly and reacts spontaneously. So, but the energy investment into doing that process to begin with is to electrolyze the salt water into the base, into the sodium hydroxide. And the Earth would normally do that with photosynthesis. So the energy going in to produce base in the ocean for the critters to uptake carbon is photosynthesis, the solar energy. Okay.
So let me get this right. The process that you're talking about is putting salt water in a vessel and electrocuting it.
Yep.
And exactly. Pulling out chemicals from the seawater and making seashells out of it. Is that roughly
kind
right?
Of, roughly, yeah. Yeah, I wouldn't necessarily make a seashell out of it. Actually, I mean, again, I'll maybe point you to the website to show you the exact two equations that are going on chemically. Probably get lost on listeners right now, but you're producing sodium bicarbonate. Sodium bicarbonate is like one of the many salts that dissolves in water. And one of the things that you can do, and that I've been wanting to do, is it's actually beneficial to both groundwater and streams because it's a buffering agent. It reduces pH changes. The pH that will equilibrate in water if you just let sodium hydroxide build up to whatever concentrate, not sodium hydroxide, I should be careful, sodium bicarbonate, baking soda. If you let water have as much sodium bicarbonate, baking soda that you want, that's going to stay in solution, the pH of that solution without other acids and all that would be 8. So a pH of 8. It has the extra added benefit that when you add acid on one side, it neutralizes the acid into CO2. If you add base to the other side, it'll actually produce carbonate and settle out as carbonate. So it's a buffer. It prevents pH changes. And that's very beneficial in a whole wide range of environmental areas. So ocean water, seawater, it's all benefited by having high bicarbonate levels. So the indirect process of running CO2 through a base like sodium hydroxide is to produce sodium bicarbonate. That can be discharged. That can be discharged right into a riverway, right into groundwater, right into the ocean, and it would have a beneficial effect as long as it's purely sodium bicarbonate. Don't get me wrong. Any kind of industrial product, you have to be careful. There's contaminants with that. But the sodium bicarbonate by itself is harmless. In fact, it's very beneficial. It would clean up acid drainage sites or acid rain problems, because it would raise the pH of the water in acid-affected lakes, for instance. So that's now if you were able to put a ton of bicarbonate into your groundwater, into your lakes, and into your rivers, it would ultimately stay in solution and wash into the ocean. And guess what would happen to it? It would be naturally taken up into shells and put on a seafloor. So you don't even have to be sitting right next to the ocean to get this carbon into the water as bicarbonate and send it down to where it's going to be sequestered on the seafloor.
Wow. So completely naturally occurring process. So the problem with my synopsis was that it's actually more like baking soda and less like calcium carbonate, which would be seashells, right?
Right. Yeah, seashells would be the calcium carbonate. Let's put it this way: the sodium bicarbonate, which is baking soda, is very soluble. You can take a teaspoon of baking soda. It's actually it's almost the same solubility as table salt. It's that easy to stir in solution and have it dissolve. The solubility of calcium carbonate is four orders of magnitude less. So we're talking 10,000 times less soluble to try to dissolve calcium carbonate. So once you lock that into a calcium carbonate salt, it's pretty solid. Now calcium carbonate reacted with acid, yeah, you bet. That's going to kick off CO2. Geologists in the group, you put acid on a limestone. We call it the fizzies, the rocks that fizz when you drop acid on them. The saying in geology was, when in doubt, drop acid. So if you didn't know what your rock was, and you had a suspicion that it might be calcium carbonate, you drop acid on it, and if it fizzed, well, that fizzing is CO2. That's calcium carbonate plus acid going to calcium chloride, basically, and CO2. And so, but otherwise, without the interaction of acid, that is a very stable compound, which is why critters make their shells out, which is why it can stay on the seafloor for a very long period of time and become part of the bedrock. So
that's incredible. By the way, everybody should check out John's website. It's canwenow.org. It's very informational. It has a lot of good stuff on there, so definitely go check it out if you want to learn some more about this. In general, John, thank you so much for being our next guest on our show. And I just wanted to mention, you should also check out Nevada Conservation League's Facebook page. That's just search Nevada Conservation League on Facebook. And once again, this was the Sustainability Podcast from the Nevada Conservation League. Thanks so much for hanging out with us.
Yeah, very good.
Perfect.